Okay, so first of all, I would like to thank the organizer for the invitation. It's a big honor to give a talk here. I would like to speak about two special models of the band matrices. The first is the usual random band matrices. So we consider box in ZD in any dimensionals, and we numerate the matrix elements by two indices which lies in that box. And we assume that these elements are independent except the conjugation. So we consider Hermitian matrix. So only conjugate elements are correlated, and the correlation function is this J. And in principle, it can be any function with which, first of all, of course, positive, and with the sum over I equal to 1. And the second, it should be small if you consider I and j far from each other. So if difference between I and j is small, then j should be also, if difference is big, then j should be small. Here in this talk, I consider a especially convenient choice of j, which is given by this function. Here w is a big parameter, which then we send to infinity. Delta is a discrete Laplacian with, here I consider the Neumann boundary condition on 1 and d. If we consider d equal 1, then this variance that we have here is exponentially small when the difference between I and j is bigger than w. That's why these matrices can be considered as a band matrices of the size w. So we have situation when this is 2w. So here we have a finite difference, and then it decreases exponentially. The second model that we consider here is a Wegener type model. What it means? It means that we have, again, we have z box of 1 over z box lambda, and 9 we assign to each site in this box a doubly dimensional complex vector space kj, and that no, sorry, yeah, it's this red button too. Yeah, okay. So this, and let k be the direct sum of all these spaces. From the physical point of view, this means that we assign to each point, each atom in this lattice, a W valence electron. So what is our model? We can start from GUE matrices from M to M, and then consider this like a block matrices of blocks W times W, and then we multiply the variance for each block to some positive variable Jij. So this means that we have these block matrices, and the variance in each block is constant, and variance differs from one block to another block. And of course, it's again Hermitian. Such models were first introduced and studied by Wegener, and usually it's called local gauge invariant because they have a property that if you consider the probability distribution of such matrices, then it's invariant under the conjugation of unitary matrices, where this unitaries is a direct product of unitaries in each space Kj. So you take unitaries in Kj, then have direct product, and then this measure is invariant under such transformation. This is called local gauge invariance. So in this talk, I consider case of J equal to Z1. So that means that on the diagonal, your variance is 1 over W, and for the off diagonal, it's like a Laplacian times alpha divided by W. So again, for 1D case, this means that you have the following matrices. It consists of blocks W times W. All blocks except 3 diagonal are 0. Here we have GUE matrices as usual, and with variance alpha over W, 1 minus 2 alpha, maybe it's the right because of a partial y 1 minus 2 alpha over w. And here we have again a Gaussian matrix with independent variance, and this variance is alpha over w. So in principle, it can be also considered as a band matrices because non-zero elements are only on the band of size 2w plus 1. So density of states for both models are well known. It was obtained in the paper of Molchanov and Pastor in 1992, I think, that the density is again a Wigner semicircle law. But the more interesting question is what about the local statistics for these ensembles and in general for ensembles of vector matrices. So the K physical parameter of this model is the localization length, so is the typical length K of the eigenvectors of this model. Again, the system is called delocalized if, roughly speaking, the localization length comparable with the matrix size is localized otherwise. For the physical point of view, delocalized system corresponds to conductors and localized to the insulators. So there is a conjecture for the band matrices, which belong to Kassatir, Molinari, Zayev, Mirlan, and Fedorov in the early 19th, that for 1D case, we have that this localization length should be grows like w square. So which means that where in w we can see the crossover here. So for w which grows faster than square root of n, we have the localized states, and for w which grows slower than square root of n, they are localized. In terms of eigenvalues, this means that we have a Poisson statistic for w grows slower than square root of n, and Dewey statistics for w grows faster square root of n. For in 2D case, the localization length is expected to be exponentially growing in w, and so the critical value of w comparable with n is n equal to log w. For d bigger than 3, the system is expected to be delocalized in this case. But at the present time, only some upper and lower bounds for the localization length are proved rigorously. So from the localization sides, it was proved that L smaller than W in the eighth power. It was proved by Schenker in 2009. And there was also recent result of Erdős-Knollers which proved from the delocalization side that L bigger than first that W bigger L bigger than W in 7/6, and then with also Yao Yin in 2012 proved for the same for 5/4. But in this case, as far as I remember, the bounds are not uniform n. The questions of order of localization length are closely related to the universality conjecture for random matrix theory. So let us briefly remind what is this. So the main object of the local regime is K-point correlation function. We consider the expectation of Z sum, where phi is some Bowden continuous and symmetric function, and this expectation is given by integral of phi times correlation function over all space. And the conjecture for the Hermitian case in the bulk of the spectrum, and maybe it's better to say to the case where we have delocalized agent states, states that if we consider take one point inside the spectrum and consider the small fluctuation of that point for all lambdas, so we consider all lambdas here in the 1/n neighborhood of the sum points inside the spectrum. In our case, it's -2, then the following limit is determinant of the sign kernel. This is the strongest way to formulate the universality conjecture. There are many not so strong ways, but this is one of that. For the edge of the spectrum, you need another normalization here, and here you should obtain the Tracy-Widom distribution. So here you have the Airy kernel, and for the edge of the spectrum, that result is known. This is the result of Sasha Sodin, and you can see here the crossover, and the critical value, as far as I remember, is n in 5/6. Yes, yeah. So, but for the edge of the spectrum, the moments method works very well. Unfortunately, it can't work for the bulk of the spectrum, so you need to invent some new methods. I want to speak about one of such methods. I can't say that it's new, but for many mathematicians, it's maybe kind of new. This method is Grassman integration, or supersymmetry approach, as usually it's called. And this method potentially is very powerful and widely used by many physicists, but unfortunately, mathematicians can't understand it in a rigorous way. Not everything, but some points they can't understand now well, but for some points there is a good analysis. So I want to briefly remind what is Grassman integration or supersymmetry approach. So we consider sets of 2n independent variables. It's psi j and psi j bar. Bar is just notation, so they are really independent. And we assume that all these variables anti-compute with each other. Yes, and so they form some Grassman algebra A. We can also define a function of Grassman variables. So if we consider the element of this algebra, this element, of course, is just a polynomial of Grassman variables, since we can't obtain any products bigger than 2n. Then, if we take any, it's not necessarily analytic, of course, we can take sufficiently smooth function, and if we want to define f at xi, we want to define it like we take the Taylor series at the point A and substitute xi minus A. So then, of course, the relation that we obtain is also a polynomial, so this is the elements of our algebra A. So, for example, if you want to compute exponent of psi bar psi, this is just 1 psi b psi bar bar. If you want to compute the exponent, I prefer the exponent, it's before I use it for exponents. That's why I want to show this cases. So consider the exponent of now 2 by 2 quadratic form. Then you have this 1 plus quadratic term, and here you have fourth term, and this, of course, is very familiar because it's just the determinant of matrix A. So also, following Berezin, we can define the formal operation of integration over the Grassman algebra. So we define it like integral of the constant is 0, and integral over psi is 1. Psi over psi is 1. The multiple integration is a repeating integration, and of course, we can extend it to the whole algebra by linearity. So what does it mean? It means that if you have some polynomial of psi's and want to integrate over psi 1 and so on psi k, then the integral is the top coefficient, roughly speaking. This is just what it means. And the main important formula that we have here in this Grassman theory is that if we want to integrate the exponent of quadratic form, then we have determinant of A. It's easily can be. So here, if we integrate over all psi's, we need the top coefficient, and the top coefficient is just the determinant. So it is well known that if you use the Gaussian integration, we have here -1. So this a complement formula to the Gaussian integration, roughly speaking. So also important thing that we can combine now the Gaussian integration and this Grassman integration. We can define the super matrices. What is this? Is the matrices, block matrices. Here A and B are usual complex matrices, and sigma and rho are Grassman variables, Grassman K by K matrices. And also we want to define the vectors phi with K Grassman variables and K complex variables. Then in principle we can construct a linear algebra on such a vector space and define many operations. In fact, we can define similar equality, some similar thing like a determinant and trace of the matrices. So then if we want to integrate quadratic form on these super matrices, we should combine Gaussian integration and integration with Grassman variables, and then we obtain not the determinant, but we obtain super determinant which is analog of the determinant in this linear algebra, and this super determinant can be defined as follows. So this is all the formulas that now we need from the Grassman theory. So let's now return to the main question. So we want to prove the universality conjecture for that model that we have, for some models of band matrices. To prove the universality, one thing that one can do is to obtain the control of the CTS transfer, so trace of the resolvent, for epsilon which is of order n minus 1. If you obtain that control, then you can prove the universality. So what is Stieltjes transform for trace of the resolvent here? It can be obtained, of course, by differentiating the ratio of two determinants. So roughly speaking, we want to control that expression. It's important here that we want absolute value square, not the square, but absolute value square. It's very important, and this means that we should take different sign of I epsilon here. Here should be minus and here should be plus. From this, and here you can see that we have two determinants in the numerator and two in the denominator. And so if we want to try to obtain the integral representation using the Grassman theory, we want to use Grassman variables, or Fermions variables, like it usually calls physicists, for that determinant, and usual complex variables for that one. So these two determinants usually call the fermion-fermion sector of the full model, and this two is the boson-boson sector of the following model. And since you have the common expectation for this determinant, after expectation you certainly mixed boson and fermion sector. This means that you obtain also boson-fermion sector, or fermion-boson, it's how do you like. So from this point, it's easy to see that if you want to study the full model, it's a good first step is to study just one sector of this model. It's more interesting to study the fermion-fermion sector of the model because it shows it's more rich, roughly speaking. It shows more from the behavior of the eigenfunction. So first question that we want to discuss here is the second correlation function of the characteristic polynomial. So now we consider just two polynomials, and again want to understand the local behavior of this polynomial when lambda1 and lambda2 belongs to the 1 over n neighborhood of the point inside of the spectrum. So this question is of independent interest because, first of all, these polynomials, characteristic polynomials, connected with many other branches of mathematics, for example, with zeta, even with zeta function. So it's also interest independently, but another interesting case that this object is also universal in some sense. In what sense it's universal, I want to explain here. So for GOE case, this even for 2K determinants, the behavior of this function is well known. And here you obtain, again, the determinant of the sine kernel. But you can see here that this is not the same determinant that you obtain for the usual correlation function. So you have 2k of xi's. You divide it by 2 parts. You form a determinant of one xi and another xi. And then divide by 2 van der Monde determinants of the one half of xi's and another half of xi's. It seems that it's depend on the distribution of for the two set of xi's, but it's not. It's easily to understand that it's not. In what sense I can say that this is universal? For example, for the beta invariant ensemble, so for of course the Hermitian case beta equal 2, so as we talk for GOE, it was shown by Brzan-Hikami in 2000 and Ferrer-Strachov in 2003 that we have the same behavior, except one moment that this Cn depends on V, but it depends only on the first derivative of V. V is the potential that we have for matrix model. The same result is valid for the general Hermitian-Wigner and general sample covariance matrices, so with any distribution, if it should only have enough moments, because when you compute the expectation of the determinant, of course you need some finite moments condition. And in this case, in case of Hermitian-Wigner and general sample covariance matrices, you obtain the same behavior, except one point. This Cn now depends on the fourth moment of the elements distribution, but does not depend on any higher moment. So it's depend. You can take any fixed k, but the behavior depends only on fourth moment. So it's this is also the manifestation of the universality, and this fourth moment you can comparable with the fourth moment theorem of Tao Wu paper, for example. So it's something like. So if we consider another symmetry class, so GOE case, so real symmetry class, this behavior for GOE is also well known. And as for the usual correlation function, this again you have here not the determinant but the Pfaffian, and this determinant that you get here is a derivative of the sine kernel divided by van der Monde of whole variables. Again, this is expected to be a general fact because for special for case k equal 1, for the it's not Hermitian, it's real symmetric Wigner and general sample covariance matrices. It was obtained in the work of Kosters. That this is also true, and again this Cn depends only on the fourth moment. But of course for k equal 1 it's not so surprising that this depends only on fourth moment. The surprise really here, so that for any k you can take very big k, but the dependence only on the fourth moment. For of course for k equal 1 there can't be any dependence for some other model. But for the orthogonal case, as far as I know, it's nobody proves that. So in the case of the model that I consider, here I consider the first model. So we consider the random band matrices with this minus w square Laplacian plus 1 variance. And the result is the following. If we normalized the determinant, the second correlation function of the determinant in the proper way, then in the regime where we expected to see the delocalization, so in the regime where w squared grows faster than n, we get the sine kernel that should be there. And for the real symmetric case, again, we have the limit in the same regime, but of course the kernel is different. This kernel is just this derivative that we have here. And we have here, again, the limit, but it's other kernel. In the regime where is w squared smaller than 1, we expected to have, except of this kernel, not this kernel, but just 1. So we expected that this answer is 1 here and also here. So as you can see, even on characteristic polynomials, you can see the crossover. And in case of characteristic polynomials, you can go very closer to the crossover point. And this is good thing of good property of the characteristic polynomial. So what I need to say something about the proof. So where we use the Grassman integration, it's just only to obtain the integral representation. Integral representation, there are very standard procedures that allows you to obtain the integral representation. Physicists know this very well, and these procedures are totally rigorous, so they are not problem. It's just Gaussian integration, Grassman variables, nothing else. And then you obtain such integral representation. So here xj is 2 by 2 Hermitian matrices. Your xi is so now xi is that one. So we now speak about the Hermitian case because the real symmetric case is very similar. It's not so important what we have here. So for Hermitian case, we have this 2 by 2 matrices, and here's xi hat is xi times matrices sigma 3, so 1 minus 1 matrices. And maybe I should emphasize here that in principle it's not important to have so this is the formula for the dispersion of this form. But in principle, it's not so important to have this. So if you take other j, you can also obtain the integral representation, but this j looks, this integral representation that you would obtain if you try, looks like, so here you accept of this Laplacian of x that we have here, you have just sum over j and k trace of xj xk times jjk inverse. So this is j inverse jk. Everything else is quite similar. But from this formula, you can easily see why it's so useful to have this model, because when you inverse J, you have just 3 diagonal matrices. That's why it's very useful here. But in principle, the integral representation you can obtain for any J. Another thing that it's not important, that here is the representation of 1D case, but in principle it's not important to have here 1D. You can sum just over nearest neighbors over the whole box, and no problem, you have an integral representation. Here there is no Grassman variables, you integrate it out. So from that moment there is no Grassman, it's just usual complex integral, and the main problem is how to analyze that integral. So you can use some analytic methods, for example, steepest descent analysis, and you can analyze this. The big problem that you have here is that if you try use a saddle point analysis, the Gaussian approximation to that measure that you have here is not positive. So you have the complex coefficient there, so you can't use then the positivity of the measure. It's a bad point here, but in principle, so what I want to say more about this model, I want to say that this model closely related to the classical Heisenberg model. Now I try to explain why. So let us change variable. So we have the Hermitian 2 by 2 matrices. Let us change variable and diagonalize these matrices. Then, of course, we obtain some Vandermonde. It's not important here. And our integral is now over the eigenvalues and over the higher measures over unitary group U2. Then, as usually physicists do, go to the sigma model approximation. From the mathematical point of view, this means that we fixed eigenvalues, so the elements of matrix AJ, which is diagonal here, to the saddle points, and leave only these unitary transformations that we have here. So saddles is very simple here. It's just plus minus p rho, where the rho is the density of states, so the local, so the semicircle law. And so if we fix in aj equal to a plus and bj equal to a minus, we get that our xj now is p rho times these matrices where sigma 3 is 1 minus 1. This corresponds, since uj is a unitary 2 by 2 matrices, this can be seen as a vector of the sphere. And after all these things, so we fix the eigenvalue. So for example, this is fixed now. This case, this part is also fixed because it's unitary invariant. So we have uj near xi when we write the quadratic term, and here in the Laplacian. So if you try to see this, you get the following relation. Instead of this integral, you have the following. You have here this p square rho square w square. Here you have the scalar product of these two vectors on the sphere, -1, and here is some external field which is small. So this is directly classical Heisenberg model, in this case for 1D, but if you consider many D case, you obtain the classical Heisenberg model for 2D, 3D, and so on, so it's not a problem. For 1, and the w square corresponds to the inverse temperature, so it's like beta in usual statistical mechanics. So for that model, the result states that if you, in the regime when w square bigger than n, that this limit is just the mean field. So this means that if n, your size of the box smaller than w square, then all your spins are ordered, and this constant, and so you have just the mean field model here, which gives you actually integration over these unitary groups. One unitary group gives you the signed kernel. In the case of the real symmetric symmetry, you get completely the same situation, only different that your Sj now is not on the sphere, because instead of unitary groups here, you get the symplectic symmetry. So you have almost the same, but these vectors will be on some other manifold with the symplectic symmetry. But the result is directly the same. Yeah.
With this formula, can you say if w squared is much less than n, you will get the result?
Yeah. Yeah, here it can be done. Yeah, but of course the mathematical question is not only this. For 1D, Heisenberg is not very hard. As a mathematical point is how to control, oh, it's not, maybe how to control these eigenvalues and mix it together with the unitary group. So this is mathematical point. But from the physical points of view, it's just classical Heisenberg, because, okay. So let us speak now about the result in the full model. For the full model, it's more convenient. To have not that model, but the model with block matrices. So I recall that for 1D case, we have these block matrices. Here's dispersion over W. Here is alpha over W, and so on. And in this case, you can consider also the full model, so the real correlation function, but first for the fixed number of blocks. So it means that the size of your band is comparable with the matrix size now. So in this regime, so if you fix the number of your sides and just try to send W to infinity, you have the correlation function converge weakly to the determinant of the sine kernel for 2 by 2 is just 1 minus sine square. And this is true for any lambda 0 smaller than square root of 2. The condition of this one is just technical, and this is not very important here. Also, the condition of the finite lambda is also not so important there, because in principle use the same methods that you need for that result. You can obtain that for n which grows like a very small power of W, you have the same. So in principle, it's not so important that the number is finite. moreover, for d equal 1, the same method is expected to work for number of sites which is smaller than square root of w, which, if we return to the full matrix size and the width of the band, corresponds to this regime. But this requires more delicate technique. It's a little harder to obtain because you need to work with this infinitely many variables, and you need to work with this unitary group, so it's not so simple. So also I should mention that this result, there is not important that you in 1D, you can obtain this in any dimensional. Moreover, it's not so important that you have lattice. You can take any regular graph with a finite degrees of the vertices and prove the same thing. So maybe I need to say what is the problem here for 1D, for other dimensions. Maybe I should say about this. So return for the moment for the determinant. As I told before, you have in sigma model approximation, so in physical meaning of that model, you have the Heisenberg model. But for bigger d, you even can't, we don't know even this. So if this is just a first step to obtain that result is to understand what we have here. If somebody understand how to obtain that, then maybe there are some opportunity to have that result for 2D and 3D or 3D or more. So let us now return to the full model. What is the difference between full model and this fermion-fermion sector? The integral representation that you have here looks, roughly speaking, the same. You have here, again, this is another model with this alpha. That's why you have not w square here, but w near the Laplacian and w near super trace. So you have, roughly speaking, you have something like this Laplacian. Again, you have this one, and again, you have the product of the determinant. But now it's not the determinant, or your matrices F here is not Hermitian, but it's a super matrices which have the following form. Uj here is a 2 by 2 unitary matrix, and rho j and tau j is 2 by 2 matrices of independent Grassman variables, and bj here is 2 by 2 positive Hermitian matrix times 1 minus 1. So it's this matrices that have hyperbolic symmetry. And super determinant here, I recall this is this one, and super trace can be defined as a trace of uj minus trace of bj. All others are completely the same. In what usually physicists do to study this model, they again come to the sigma model approximation. So they diagonalize these matrices by the super unitary group, and then they fix the eigenvalues of that matrices and integrate only over this super. So they obtain this Heisenberg model, but that spins are not usual spins on the spheres, but some spins on the some super domain, supersymmetric domains that you have, and the symmetry that you have here is not usual symmetry, it's supersymmetric symmetry, and even not compact symmetry, because the symmetry of bj is hyperbolic. So, but unfortunately, even come to the sigma model in a rigorous way is not completely understandable how to do this now. So, not only the studies of that model, but on rigorous study of that model, but also how to go from this model directly in the rigorous way to that model, we also don't understand. So the mathematical way, except that I know now, is try to integrate here over the Grassman variables, because what usually physicists do, they do the saddle point analysis directly in this expression, and they write the saddle point equation for Grassman variables too. They write both for boson variables and for Grassman variables. Then they do some computation and obtain that this everything okay. Unfortunately, we don't know how to do it rigorously. So the only point that we can do is try to integrate over the Grassman variables. For the determinant case, you can integrate over the Grassman variables directly, and you obtain just these Hermitian matrices and no Grassmans. Unfortunately, here it's not so simple to integrate over Grassmans. So if you try to do it, you get something like this. So here is the same. So here you have the same operator as for determinant, but for these unitaries UJs. Here you have the same expression for these matrices with a hyperbolic symmetry. And so this corresponds to fermion-fermion sector, and this the same as for determinants. Here it corresponds for the boson-boson sector, and this integral that you have, that expression that you have here, corresponds to boson-fermion sector. And first term of that is easily to obtain. So what you can actually do, everything here is just expression of Grassman variables. You can expand it into the series. It's just a final polynomial. So then you try to compute the terms that you have there. And the first term is can be computed very easily. It's just the determinant of such form. So you have here Laplacian plus 1 plus this matrices inverse. On the diagonal, you have 2 by 2 blocks or 4 by 4 blocks, which is tensor product of your matrices. The main problem in this, of course, I can analyze this one. I can analyze probably that one for the regime that I need. But the main problem here is that at the saddle point, this term, I don't say now about this term that you also need to understand, but even this first term is 0 and the saddle point, so you need to expand it. If you try, and this is not very simple because then you have the minors, since if W grows together with N, then minors also grows, and so this expansion looks not so good. But I think that for the case when for the case when W grows faster, everything can be done here by the same technique. Okay. This one, in principle, I can explain. So, as I told you before, the main problem here is that this determinant is 0 into the saddle. Let's assume now that we have no unitary groups. Let this uj and bj be just the diagonal. That this determinant is a 4 determinant. And 2 of them is 0 at the saddle and 2 of them no. So, roughly speaking, you need to expand such determinant. And here you have diagonal element, something like a plus plus some fluctuation of your variable. Let's call it uj tilde times a minus plus bj tilde. You have such diagonal. When you try to if you put uj tilde and bj tilde equal to 0, this is 0. If you try to expand this determinant, you have the minors of the determinant of such form. And if you try to compute, so let us assume that we take off k rows and k columns, then it grows like n over k, roughly speaking, the minors that you have here. And you need the additional number of w to cancel this growth. And this number of w, so this, if, now where is it? So if your n is just your lambdas that you have here, so if n grows not very fast, then the additional number of w can cancel your, let's say. So what you have, this uj actually, they off-road square root of w. You can see this from here. you have big parameter W, so your fluctuation should be as average in saddle points 1 square root of W. And so if you have additional W to cancel this, you can work with this expansion. If you don't have this number of W, then you have the expansion, but the elements of that expansion are gross. And so you need very explicit analysis to understand that they really cancelled. So maybe I need to finish there because we changed the questions. OK, thank you for your attention.